Our next speaker is Diego Saikin. Where is he? Here he is coming. So he's one of our community members, and he's a guidance navigation and control engineer at Astroscale. But he's going to talk about a PhD work that he did and was accepted, master degree, sorry, that was accepted also in ICRA, right, back then. A very interesting work he did. I got to know him a couple of years ago, and I'm sure it's going to be awesome. So thank you.
Thank you. Thanks. Yeah, my name is Diego. I'm going to talk about a couple of projects I worked on, and I want to thank the Israeli robotics community and especially Amit for hosting me and allowing me, giving me the platform to share what I worked on. What do I? Space. Okay, so wildfires. Woo. Okay, there's a big discussion whether wildfires should be fought or not. But the fact is that there's a very clear trend in the last few years that wildfires are becoming more frequent and more intense. This is because mostly of global change, climate change, that makes a very prolonged droughts. Now, drones are being used to fight wildfires, but only on secondary tasks, like monitoring, detecting the wildfires, maybe even logistics for the firefighters, but not in the main task, which is extinguishing the flames. And my project, when I started working it, I was studying for my master's, and I was looking for a topic, and we still had the trauma here. A couple of years before, there were big bushfires in the Carmel, if you remember. And I remember all the air forces of the world sending their aid to Israel, and I was like, why are they not sending swarms of drones 24/7? It seems that it's more complicated than that. So I started working on all this crazy idea, and in the university they told me, relax. This is just a master's thesis. So since my field of expertise was path planning and control and all that, so I moved into the trajectory to tackle these fires. Now, arriving to a wildfire quickly is it's of uttermost importance in order to avoid that a small and manageable fire will become a mega fire. So we have two types of, for aerial firefighting, we have two types of aircraft, winged airplanes, or all the rotary wing, which is all the copter, like helicopter, multicopter, et cetera, et cetera. No, we don't use multicopters now, but you will see why. So current manned firefighting is extremely expensive because you have to have very skilled pilots and trained all the time, and it's extremely dangerous. These maneuvers, like because of the sloshing of the water inside the airplanes, they can stall. In addition to all that, they cannot operate in bad weather at night or any bad visibility conditions. Now, fixed wing aircraft are more efficient in anything related to payload. They can carry a larger payload faster and to longer distance. But rotary wing aircrafts have the big advantage that they can scoop water from any concentration of water, any pond, even a pool, whereas fixed wing aircraft need very large extensions of calm water in order to scoop water. The same goes for dropping. By the way, airplanes cannot properly drop water on any terrain, whereas helicopters can. And the team I was working on, the university, they work with multicopters. So it's a good match. So what we want to do is actually to enable a UAV to drop a relatively large amount of water or any fire retardant precisely on a fire focus and to drop it as close as possible. Why do we want to drop it as close as possible? Let us imagine you want to drop water on a fire. So you fly above it, drop the water, and that's it. But if you drop it from very high above, the water will either evaporate or disperse, or both of them actually. If you drop it too low, you are in danger of burning the aircraft, right? You're exposing it to very high temperatures and it will damage its structure unless you do it very, very quick. Think about you holding a candle and passing your finger through the flame. If you pass your finger quick enough, you will barely feel the heat, right? So if we want to do this with a drone, we have a problem that it could be like a short blanket problem, right? A drone, in order to move forward, has to tilt its whole body. But in order to maintain flight, you need that at any given moment, the vertical component of the thrust will be equal or larger than the combined weight of the drone and the payload. So the problem is that if you want to drop the payload very low, that means you have to fly fast, but it means you can carry a small amount of water. On the other hand, if you want to carry a large amount of water, it means you can fly very slow, so you have to drop it very high. Can we make some compromise? And the idea is that, yes, if we actually disregard the need of maintaining flight, if we imagine engaging in a very risky maneuver, you can tilt the drone even 90 degrees and exploit all the thrust to accelerate forward. The drone is falling. It's totally falling, but it's also accelerating. At some point, you drop the water on the fire. You drop the water. You make sure that the moment you drop it, it will hit the fire. You have to drop it in the exact location, and then. But now you're light, and you can recover. If you think about it, when I started searching for literature to deal with mass variations, all the existing literature was about mitigating the effects of mass variation, considering mass as disturbance. But what we do here, it's actually exploiting the expected variation in mass to our advantage. We are able to recover because the drone is light later. So we approach the problem as an optimal control problem, in which we generate a time series of state vectors, which include the position and velocity and the tilt angle of the drone on different time along a trajectory on different time steps, the heading angle of the whole maneuver, and the releasing signal. What we want to minimize here is the overall time of the trajectory. And at the dropping point, we want to minimize the altitude and maximize the horizontal speed. The constraints we have is, of course, in order to go through this trajectory, we have to obey the dynamic model of the drone. We cannot do anything. It has to match the physics. We have to make sure that the payload, once released, it follows a perfect ballistic trajectory and hits the target. We have all kinds of, well, after finishing the trajectory, of course, we have to avoid colliding with the terrain. That means we have to be at a higher altitude and rising. And through all the whole trajectory, we want to avoid a minimum height above the ground to make sure we're not colliding as a safety measure. So this is the result of the optimization. This is the shape of the path. It's actually not something I designed. It's the outcome of the optimizer. What I just told you before about tilting the drone, it was my imagination. But after describing the problem to the optimizer, this really was the outcome, not surprisingly. We divide the trajectory into 3 phases. The first phase, the red one, is the approach phase, in which we are accelerating and falling. The green phase is where we are releasing the payload, and the black phase is the recovery. The solution for this, I described the whole problem in 2D on a plane, right? And the reason is to make it because of this dimensionality, the problem becomes much smaller and much more manageable. So the optimizer is able to output a solution much quicker, and it allows the future implementation into a model predictive control. For those of you who don't know, model predictive control consists in mostly recalculating a trajectory and executing one or a few steps and recalculating it and updating the trajectory over time, okay? So in order to still provide a 3D solution, what we do is we can rotate this whole plane. We take into consideration environmental parameters. This is not done in, the joke about the spheric horse. This is not done in yeah, exactly, in vacuum. This is not done in vacuum. We take into account aerodynamic drag and terrain gradient. Of course, it's not like a real terrain gradient, but it has to be like a smooth surface, but it can have any orientation, any tilt. And also consider different releasing mechanisms. The first would be like dropping a balloon or a container with water. The second would be a constant flux pump. And the third would be like having some kind of container with a hole on the bottom. Now, after we did all this simulation, the results at the end were very similar to each other. So when we had to proceed for further experiments, we chose to do only the step and releasing weights at an instant. So first we did some simulations in MATLAB. Then we proceed to Gazebo. And at last we did 2 test campaigns in a test range in the outskirts of Prague. The first one was more mild with higher safety measures. We actually dropped from a higher distance at lower speeds. We incrementally raised the weight. It was mostly to make sure that we are not going to crash and that and to identify sources of error. For example, these disks we were using, sometimes they glided, or because of the high rotational speed, sometimes they threw the disks away. But after we had identified all the sources, so we turned all these switches off. The guys at the university were like, "Are you sure you're doing this?" Yeah. So we allow the drone to tilt like actually 90 degrees and fly extremely fast, dropping the weight. And in order to prove that we actually have the most extreme maneuvers we could possibly have, the last test was simulating a malfunction in the releasing mechanism to prove that it is so extreme that if we cannot release the payload, we actually cannot recover. Did we crash on purpose a drone on the last test? These results, after we published them, they got us to the Robotics and Automation letters for the year 2020, and also to the International Conference in Robotics and Automation. The payload was very large, was about 1/4 of the overall weight. With that, we managed to achieve velocities 90% higher, almost twice higher than the nominal speed of the drone. We dropped at 12 meters, and even then we got an average standard deviation of droppings of less than about 2 meters. So yeah, that's it. And that brings me to my second project. After coming back after the publication, everything, I was approached by an acquaintance that works in a drone delivery company. I'm not going to say which one. But they say they have this problem that if you have, like in Zipline, you have like a fixed wing aircraft dropping, they cannot drop very accurately. So that's why most of the drone deliveries that have to deploy payloads very, very accurately, they do it with drones, multicopters, or for example, these hybrid things. The problem they have is that the whole drone has to be designed for the peak power consumption, right? And all these minutes that they either hover or land, they consume a lot of power, and then their active radius gets reduced. They get very limited. So what they asked me is if basically I could come up with an idea of laying the payload very smoothly and very quickly without having the need to hover above. So the idea I came up with is it's an evolution of the algorithm I just presented before. Imagine that you're flying and approaching the dropping location. A few tens of meters before you extend the payload, you extend it with the tether, like let's say a wire, or you're flying with the thing hanging. And you start inducing oscillations on it by accelerating and decelerating. And you can coordinate the movement of the drone in such a manner that at the moment the payload is touching the dropping point, it will touch the ground at 0 speed, 0 vertical, 0 horizontal. And then you cut the tether or release it and you keep flying. So yeah, I did all the modeling. Cannot play media. Try to play it like this. Mac. I assure you this works. I mean, I didn't try it on a physical platform, but on simulations, what I was going to show you is not an animation. It's a real simulation, taking into account also aerodynamic drag. The dynamic model can also be adapted for fixed wing aircraft, not only for rotary wing. And it also can be adapted not to a fixed point, but to a moving platform, like a ship, a vessel, or a car. And it's patent pending. You will have to believe me. The reason why you saw the box, the blue box, the payload, whatever, being dragged backwards is because of the aerodynamic drag. If you change different parameters, you may in fact induce oscillations, real oscillations. It really depends on the ballistic coefficient of the payload and their atmospheric pressure, et cetera, et cetera. Of course, you have to provide a feasible set of parameters, right? If we try to imagine this being a jumbo jet trying with a 30 centimeters wire, trying to land this between the buildings of Manhattan, it will not work. But there's a certain set of parameters, most of them, that it actually works pretty fine. Yeah, it's probably giving maximum thrust. One of the constraints I can limit is the maximum thrust. Of course, I want to leave some margin to allow it to maneuver. But it depends on the weight you put on the drone and the thrust to weight ratio. So yeah, it was too good, so I patented it. So back to the presentation. Yeah, that one. So yeah, thank you. That's it.
Questions?
Yeah, questions. Okay, I dropped it on purpose about 20 centimeters below. That's what probably wobbling. It's not wobbling. It's hanging from a pendulum, and it does not suffer because it's a pendulum. It does not feel any sideways G's, only towards upwards, and it's very, very smooth, extremely smooth. Like I was fantasizing when I try this. I try to lay a glass of wine while I'm having a meal, something, and just lights a glass of wine and keeps flying. That was what I was dreaming on. No, it's not slight. The thing is it feels all the time G going upwards. It never feels any zero acceleration sideways. Sorry? No, because it's a pendulum. So it's always the acceleration is always towards the wire, if it's a wire. Of course, if you're using some kind of actuated robotic arm or something like that, you can't generate oscillation acceleration sideways.